In this video, we're going to look at computing n hat, a sub t, the tangential component of acceleration, a sub n, the normal component of acceleration, and a new vector quantity. It's called the binormal vector. It is defined to be the unit tangent vector crossed with the unit normal vector. And we're going to talk about this idea of what's called the Frenet frame. Sometimes it's called the TNB frame, and it's a frame made up of the unit tangent, the unit normal, and this vector b, which is called the binormal vector. So let's review just a little bit before we get started. Let's say we're going to assume that we're in three-dimensional space. Now sometimes we're in 2 dimensions in this class, but theoretically all the math could hold an n dimension. That would be fine. And let's say we're in 3 dimensions. So r of t has 3 components: x of t, y of t, and z of t. Now remember what r of t does. R of t takes a number in its domain, which is a subset of the reals, and it maps it to a point. In 3-dimensional space, if our vector is in 3-dimensional space, in n-dimensional space if our vector has n components, or it could be 2-dimensional space. We'll look at vector valued functions in the plane as well. So R is taking a number t in the domain and it's mapping it to a point. In 2D that would be x of t, y of t. In 3D that's x of t, y of t, and z of t. Okay, so what we would see as t increases, we're going to be traveling along some points in space. That's going to create some path or some curve. So maybe as t increases, our curve looks like this. So maybe there's some object traveling along this curve. It's going that way. And r of t is a vector. It has its initial point at the origin, and it points to a particular point on the curve. It says you are here at this location, and that location is given by x of t, y of t, z of t. Now we talked about lots of things already. If r of t is giving us position as a function of time, so it's associating time with a particular position. If I take the first derivative of that, I get the velocity vector. And velocity is going to be tangent to the curve at that point. So it's going in the direction of motion, and it's tangent to the curve. And then acceleration is defined to be the second derivative of position, or the first derivative of velocity. And that's got 2 components. One component is tangent to the curve, or parallel to the curve, and then another component of the acceleration is normal to the curve. Now, if I'm in 3-dimensional space and I've got some curve, I'm going to look at the cable for my document camera here. So maybe this is our curve in 3-dimensional space. And at some point I've got a unit tangent, and that unit tangent is pointing that way. I've actually got infinitely many normal vectors, like infinitely many vectors that are perpendicular to that unit tangent. We only want one of them. We want the one vector that is perpendicular to the unit tangent that points in the direction that we're turning. We're going to call that n hat. The acceleration is composed of 2 parts, one in the direction of motion plus another in the direction that we're turning. And we said in the last video, a sub t, that is the scalar tangential component of acceleration, turns out to be the change in speed with respect to time. So this is the component of acceleration. Acting along the direction of motion. So if a sub t is positive, we're speeding up. We're accelerating in the direction of motion. If a sub t is negative, we're slowing down. So it's like coming to a stop at a stoplight. We're still continuing to go forward, but we're just going forward a little bit more slowly if a sub t is negative. And if a sub t is 0, that means we're at a constant speed because the derivative of a constant would be 0. So that is the part of the acceleration that's in the direction of motion, and it causes us to speed up or slow down if it's non-zero. Now a sub n, through our derivation we found out it was the speed squared times the magnitude of t hat prime, not of t, but of s. And this quantity is something we haven't talked about yet, except only briefly. That's called the curvature of the curve. Now, since it's a magnitude, this is always greater than or equal to 0, because it's the length of a vector or magnitude, and that's a magnitude squared. So a sub n is always positive or 0, and this is the component of acceleration. Acting perpendicular to the direction of motion. And more specifically, it's not just acting perpendicular to the direction of motion, it always points in the direction that we're turning, n hat does. So this, when a sub n is non-zero, it leads to turning. And n hat is always, n hat of t, is always the direction you're turning at time t. So if a sub n is positive, then we are definitely turning, and we're turning in the direction that is given by n hat. All right, so it's velocity, or position, velocity, and acceleration. It's got these two parts. After acceleration, the rate of change of that is called jerk. We don't use it that often, but it's the third derivative. It's the rate of change of the acceleration with respect to time. And we were just focusing on acceleration, and it had two components, one in the direction of motion and one perpendicular to the direction of motion. But that's a very important perpendicular direction. If this is my curve and that's my unit tangent, there are infinitely many unit normal vectors. There are infinitely many vectors that are perpendicular to this line in space. This particular one points in the direction that we're turning. So if I go back up here, I go to my curve, and let's say we're talking about this point right here. My unit tangent points in the direction of motion. My unit normal points in the direction that we're turning, so we're turning that way. And then there's another vector called the binormal vector. Since this unit tangent is a unit vector and the unit normal is a unit vector, the magnitude of the binormal is the magnitude of the parallelogram that has these two unit vectors as sides. So it's actually just a square. So it's a 1 by 1 square. So the binormal vector has a length of 1. and this acts perpendicular to the plane that contains t hat and n hat. So if I'm right here, and I'm traveling along this direction, and I'm turning in this direction, that creates a little plane, and my acceleration vector is in that plane. So I've got some part of my acceleration acting this way, some other part of my acceleration acting this way, and the cross product of t hat with n hat, that's the binormal, and that's going to be perpendicular to the plane. The negative of the binormal by the right-hand rule is going to turn out to go up, and the actual binormal vector, it's down here. It's a little bit hard to see that all of these are at right angles to each other, but they are. That binormal vector is going to point down by the right-hand rule. Point your fingers in the direction of t, curl them toward n, and then your binormal is going down from that. So we've got this little moving reference frame. Everywhere we go, we've got a vector that's pointing in the direction we're going, a vector that's pointing in the direction we're turning, and then we've got a binormal vector that's acting perpendicular to both of those, and the direction is given by the right-hand rule. So it's like we've got our own little reference frame. Back at the beginning of our studies of three-dimensional space, we had x hat, or x, y, and z here, and the unit vector in the x direction was called I hat, the unit vector in the y direction was called j hat, and the unit vector in the z direction was called k hat. And we said, okay, if you're standing in the classroom, you're standing in that back corner, and you put your right out arm forward, like directly forward in front of you, that's going to be the positive x direction. And this is when you're standing here looking at everyone else in the room. And your torso is in the direction of the z-axis. And if you put your left hand out to the far left of you, that's in the direction of the y-axis. So we've got y-axis, x-axis, and then the z-axis is in the direction of your torso. And to get a better sense of what's going on, like here's the board behind me in class, this is the wall to the left of me, and this is the floor. The xy plane is the floor. So we put all of those pieces together, and we said that's I hat, that's j hat, and that's k hat. Now, whenever I think of this Frenet frame, I'm thinking of my own I hat, j hat, and k hat. This is my own positive x direction, positive y direction, and positive z direction. It's this little moving reference frame that goes with me everywhere I go. When we look at this, and we imagine ourselves here at the origin, and we imagine ourselves as sort of making up these axes. You're almost thinking of yourself as the center of the universe, and you're like, that's ridiculous. You're not the center of the universe, right? Well, not unless, we all are, right? When you're on this curve over here, you've got this frame that moves with you. So basically, you've got a frame that is allowing you to see everything from your particular point of view. If you're traveling along this path, t hat points in the direction that you're going, n hat points in the direction that you're turning, and t hat cross n hat, that is normal to the plane. We call that the binormal. And that is your little reference frame. So right here, you feel like you're the center of the universe. It's kind of exactly what we're talking about right here. Like from your point of view, that's the direction you're going, that's the direction you're turning, and that is the direction that's up and down. But as you travel along this path, it's like going on a ride at Universal Studios. That t hat changes, that n hat changes, or that b hat, the binormal vector, changes. This also reminds me a little bit of like the magic school bus. So we're traveling along this curve in space, and this little frame of reference moves with us. So our reference frame is relative. We call this the Frenet frame. And sometimes it's called the TNB frame for obvious reasons. And remember how we calculate all of these. Now, t hat is r prime divided by the magnitude of r prime, or if you prefer, you can think of that as the velocity divided by the speed. It's the unit vector in the direction of motion. Now n hat is perpendicular to that and is given by the rate of change of t hat, and then we divide by its length to make it a unit vector. So this is the unit vector, and it always points in the direction that you're turning. When I say this is all relative to your frame of reference, it's exactly, I'm being very literal. If you were on this curve, this is what you would experience. T hat's going this way, n hat's going this way, and this binormal is pointing up from the plane that contains t hat and n hat. So you're accelerating in this plane over here, and that binormal points up from that. And it's also a unit vector, and it's perpendicular to the plane containing the acceleration vector. Remember, the acceleration vector is just a linear combination of these two guys. I multiply this unit vector in the direction of motion by a constant, and I multiply this unit vector in the direction we're turning by a constant, and part of my acceleration leads to turning, part of my acceleration leads to speeding up or slowing down. So that's in that plane created by t hat and n hat. This binormal vector is perpendicular to that plane, and the direction is given by the right-hand rule. And we'll talk more about the binormal and what it means in another video, but for right now we just want to introduce the idea of the Frenet frame and this little moving reference frame. Okay, now I've given you these three formulas. You could use this to calculate the normal every time if you wanted to, but it turns out that's not the most efficient way to calculate the normal vector. And a sub t and a sub n, these scalar components of acceleration in the direction of motion and in the direction of the normal vector, the direction that we're turning. These are not the most efficient formulas for calculating a sub t or a sub n either. It's really not too difficult to find the speed and then find its derivative, but finding the unit tangent vector and then finding the arc length parameter and then parameterizing the unit tangent using the arc length parameter and then finding its derivative and finding its magnitude and then taking that and multiplying by the speed squared, all of that, like, that's a lot of work. So a sub n would actually require an enormous amount of work using this formula. So we're going to use a different approach to find a sub n and a sub t than these two formulas. These formulas are great for interpreting what a sub n and a sub t mean. This is telling me a sub t is the change in speed with respect to time, and this is telling me that the normal component of acceleration is proportional to both the curvature of my curve. If it's less curvy, it's small. If it's very curvy, it's curving a lot. If it's a very sharp turn, a sub n is large. And it's also proportional to the speed squared. So if you double the speed, that normal component of acceleration increases or multiplies by a factor of 4. So that has a huge effect on a sub n. So these are great as far as interpreting what a sub n and a sub t mean in terms of motion along the curve, but they're not so easy to calculate. So we're going to come up with some better ways for calculating a sub t and a sub n, and we're also going to come up with a better way to calculate n hat. Sometimes we'll use this formula, but we don't always have to, and most of the time we'll choose not to. We're going to come up with a different way. Okay, so to come up with that different way, let's look at our acceleration vector. So let's say we are in the plane that is created by t hat and n hat. So if we're going this way along our curve, t hat points in the direction of motion, n hat is perpendicular to that and it points in the direction we're turning, and our acceleration is some linear combination of these guys. So our acceleration vector is a constant times t hat, and we call that constant a sub t, plus a constant times n hat, and we call that constant a sub n. When we add these two vectors together, tip to tail, we get the acceleration back. Now, if I want to find a sub t, what I'm really doing is I'm finding the component of my acceleration that is parallel to t. Or alternatively, I'm finding the component of the acceleration, or I'm finding the projection of the acceleration onto t hat. So if we look at this, the projection of the acceleration onto t hat, the length of the projection was given by the dot product of these two vectors. Remember, because of that theta. We got the magnitude of the acceleration vector times the cosine of theta. But if I want this to look like a dot product, if I don't know what theta is, I have to multiply by t hat, the magnitude of t hat, and divide by its length. And we said, well, that is going to be the absolute value of the dot product of a with t divided by the length of t hat, but the length of t hat is 1, so I don't even really need that. And I actually don't want the absolute value of this. The absolute value of this is the length of that vector, but if the angle between a and t is acute, that cosine is positive. And if that cosine is positive, this component of acceleration is going in the same direction as t hat. So a sub t turns out to be this times plus or minus 1 when the angle is acute. This is positive, so its absolute value is positive. When the angle is obtuse, this number is negative, and so the acceleration, or the component of acceleration that's parallel to t hat, points in the opposite direction. And the dot product in that case would be negative. So a sub t is just this. It's actually very simple to calculate. All I have to do if I want a sub t is to find the acceleration vector and find the unit tangent and dot them. Another way to say exactly the same thing is to say that's the acceleration dotted with t hat, which is r prime, divided by the magnitude of r. Or if you prefer, since that's a scalar, you can sort of factor it out. You could say that that's a dotted with v divided by the length of v. So some people use this. I don't tend to use this. I tend to use this. But it's saying, okay, find the component of acceleration in the direction of velocity and then divide by the magnitude of the velocity. And that's going to give you the component of the acceleration in the unit tangent's direction. This is true, but I prefer to use this formula. And we also saw earlier in the other video that a sub t is the change in speed with respect to time. So that's another formula. But I think out of all of these, the most efficient formula is this one, because we usually have to find t hat anyway, which is the unit vector in the direction of motion. And I often have to find the acceleration. So if I want a sub t, I just take the dot product of those two guys. This is equal to that, and that is equal to that, but I use this one. And then we're going to use this one for interpretation. If I want a physical interpretation of a sub t, it helps to think of it as the derivative of the speed. This is really easy computationally. Okay, now similarly, if I'm trying to find a sub n times n hat, well, that's just the projection of a onto this vector n. And for similar reasons, if the angle between a and n is acute or obtuse, a dotted with n hat, it's going to give me the right sign. Actually, since the normal component of acceleration is always in the same direction as this, the angle between a and a and the normal vector will always be acute. So a sub n is the magnitude of the projection of a onto n hat, which is just a dotted with n hat divided by the length of n hat, which is 1. So that's 1. And since those are always in the same direction, except for when they're perpendicular to each other, and then it's just 0, that's equal to that. So a sub n is a dotted with n hat. That's another formula. Now, in the last video, and actually earlier in this video, we discussed the fact that a sub n is also the speed squared times the curvature, where the curvature is defined in terms of the unit tangent and its derivative in terms of arc length. This is another formula for a sub n, but I don't tend to use that either. I don't use this one because finding n hat tends to be so difficult. Remember, t hat is just r prime divided by the magnitude of r prime, or if you prefer, the velocity divided by the speed. And the unit normal is the rate of change of this, which is always acting perpendicular to that, so that's t hat prime, and then we divide by its length. Now, because of this speed in the denominator, remember speed, any kind of magnitude, is the sum of the components squared. So you take the components, you square them, add them, and take the square root. So I'm going to have some ugly square roots in the denominator of each of those components of v. And then I'm going to take the derivative of that, which is going to require a lot of chain rules, a lot of quotient rules. And then I'm going to have to find the magnitude of that, and then I'm going to have to divide something ugly by something uglier. So this is going to take a while. I can sit here and do it. I can, it's just derivatives and magnitudes. We can waste 20 minutes or spend 20 minutes calculating n hat this way. But I generally don't want to use this formula. If I don't want to use this formula, I don't want to use this formula to get a sub n. There's got to be a different way, a better way to find a sub n. And there is, just using right triangle trigonometry. So let's look at this blue triangle that I've drawn. I'm going to draw it at a different angle this time. Here's my acceleration. Here is my normal component of acceleration, and here is my tangential component of acceleration. So this is my tangential vector component, that's my normal vector component. I add those two together, tip to tail, and I get the acceleration back. Okay. With that in mind, look, I've got a right triangle. It's very easy to find the acceleration. I just take the second derivative of position. It's very easy to find t hat. I just take the velocity and I divide it by the speed. And once I have acceleration and t hat, I can take their dot product to get a sub t. Now, if I want to find a sub n, well, if I've got this side of the triangle, its length is a sub t, and I've got this side of the triangle, its length is just the magnitude of a. This length squared plus this length squared equals this length squared. So I can use the Pythagorean Theorem to find this guy. So at this point, it's very easy to find this and this and this. And if I've got these three pieces, then I have enough to find this piece. And once I find a sub n, the length of this vector, I can solve a vector equation to get n hat by itself. So let's write that down. this leg squared plus this leg squared equals the hypotenuse squared. The length of this side is just a sub t squared. Or it's going to be the absolute value of a sub t, and then we're going to square it, so then when we square it, it's going to be positive anyway, right? And then I'm going to take this leg squared, this leg, and square it, and that's going to be the hypotenuse squared. That is a scalar, that is a scalar, and that is the length of a vector. The length is also a scalar, but I'm taking a vector and finding its length, and then I'm squaring it. We assume this is known, and we assume this is known. So the unknown here is that a sub n squared. So I can use this equation to solve for a sub n, just subtracting that a sub t squared from both sides, and then taking the square root. And a sub n was always positive except for when it was 0 because of this definition here. Curvature is always non-negative. The speed squared is always non-negative. So this is always a positive number. So that means this is always a positive number. And that's the third formula for a sub n. You say, okay, there's a lot of formulas there. Which one do I use? Use this one. It's the most efficient formula on this list. Okay, that was a lot. So let's recap. Said, okay, let's say somebody is asking you to find n hat the most efficient way to compute n hat is not to use this formula. This is a good formula. It's the definition, and that's the definition of t hat, but I don't want to use it. The most efficient way to compute n hat is like this. First, compute the velocity. Then with the velocity you can compute either acceleration, or you can move on to finding t hat. But we need acceleration and we need t hat, so let's find t hat next. T hat is r prime divided by the length of r prime. So that's our tangent vector divided by its magnitude, or alternatively, the velocity divided by the speed, if you prefer to think physically. And then if you want to find a sub t, that is the scalar multiplier. We're going to take that t hat, the direction of motion, and we're going to multiply by it, and that's the component of acceleration in the direction of motion. To compute a sub t, we'll just do a dotted with t hat. Now there are other formulas for a sub t. There's this one, and there's this one. Actually wouldn't be too difficult to find that, even though there's a square root and we'd have to use the chain rule. We can use the chain rule. So we could find a sub t using this formula if we prefer. But I think the most efficient formula on this list is this one. So just take a and dot it with t hat, and that's a sub t. Okay, so we've got that. And then if I've got a sub t and I've got a, I can use this formula. I can use the Pythagorean Theorem, this side squared plus this side squared equals this side squared. I can use this formula to find a sub n. So now we're going to compute a sub n. And using this formula, we've got the square root of the magnitude of a squared minus a sub t squared. There are other formulas for the normal component of acceleration. One is this one, the least efficient formula on the list. I would never, ever, ever use that. I mean, it's there, it's equal, but don't use it. Or this formula, the velocity squared times the curvature, which we haven't discussed yet. Or it's not the velocity squared, excuse me, it's the speed squared times the curvature. This is great for interpretation, not so much for computation, because that curvature is a little bit complicated to find. The most efficient formula on this list for finding a sub n is this one. So use these ones in the box for computation and use these over here involving velocity, speed, curvature. You want to use these for interpretation. These tell us what a sub t and a sub n mean. But that's the way to compute them, guys. It's really easy to find. And then you say, okay, how does that get me to n hat? Well, this vector plus this vector equals that vector. So if I want to get n hat by itself, I'm going to solve this vector equation, a sub t times t hat plus a sub n times n hat. Add tip to tail, you get a back. You're going to solve that for n hat. So if I'm getting this guy by itself, first thing I do is I subtract this guy from both sides. So I have n hat is equal to a minus a sub t times t hat. And then we're going to divide by a sub n, which is known from the last step, provided that a sub n is non-zero. And that's going to be our n hat. This is much, much more efficient than this. I know it seems like we went through a lot of steps to get here, and we did, but all we're doing is a little bit of vector arithmetic and algebra. It's just a lot of arithmetic, a lot of dot products, a lot of squaring things and subtracting, solving vector equations. It's super simple calculations right here. These really aren't so bad. Just remember when you're taking the derivative of something like this, well, you're going to end up using the chain rule and the quotient rule a lot right here when you're taking the derivatives of all three of those components. And that's going to get you t hat prime. Then you're going to have to find the length of that, and you're going to have to divide by it. So there is algebra and calculus here in this formula, but there's a lot more calculus, a lot more differentiation here than there is over here. Here I just have to find r prime and r double prime as far as calculus is concerned. And then I just use this vector arithmetic to find a sub t, a sub n, and n hat. So let's apply this in an example. I'll show you how efficient this is. And then once we have n hat and t hat, we can take their cross product to find b hat. That's that binormal vector. And remember what the binormal is. It's a unit vector perpendicular to the plane containing our acceleration vector. Our acceleration has a component in the direction of motion and a component in the direction that we're turning. That defines a plane. The vector that's perpendicular to that plane is either the binormal or the negative of the binormal, and the direction of the binormal is given by the right-hand rule. We're going to talk more about that direction when we talk about rates of change in the Frenet frame in a different video. Okay, so let's say this is our r of t, and we want to find t hat, n hat, and b hat at a particular t value. So we're going to use our list to find n hat as efficiently as possible. Okay, so the first thing I want to do is find the velocity vector. Velocity is just the derivative of position. And so you just take the derivative of the vector component by component. Very easy. Derivative of t is 1, derivative of t squared is 2t, derivative of 1/3 t cubed, that's 1/3 times the 3 times t to the 1 less power. 3's reduce, and you just get 1, 2t, and t squared. Okay, that's velocity. If I want acceleration next, acceleration is the second derivative of position. Just take the derivative again. So I get, oh whoops, I already did it. Derivative of 1 for my x component, derivative of 2t for my y component, and derivative of t squared for my z component. Derivative of 1 is what I was doing in my head, 0. Derivative of 2t is a 2. and the derivative of t squared is 2t. Now the unit tangent vector is r prime, so that's a tangent vector that points in the direction of motion, divided by the magnitude of r prime. Or if you prefer, you can think of r prime as the velocity. So we're going to take the velocity and we're going to divide by the magnitude of velocity, or the speed. My velocity vector is right here, so it's 1, 2, t, and t squared. And the magnitude of velocity is this thing. We take the components, we square them, we add them, and take the square root. So I've got 1, 2t, and t squared. Those are the components of my velocity vector. And I'm dividing by 1 plus 4t squared plus t to the 4th. Okay. So this is t hat. You can see why I don't want to use the formal definition of n hat. Well, I hope you can see that. If I want to find n hat using this definition, I've got to take the derivative of this guy, which involves taking the derivative of this component, and this component. And then when I'm done with that, I need to find its magnitude, and then I need to divide by it. And that's a lot of work, and probably a lot more work than I want to do. So we're going to use this more efficient approach to find n hat instead. Okay, so now we're going to find a sub t. And a sub t, that's the tangential component of acceleration. That's just a, the acceleration vector, dotted with t hat. So I'm finding the projection of my acceleration vector onto the unit tangent. So that means I'm taking this very simple vector, 0, 2, and 2t, and I'm dotting it with this. It's going to take longer to write it down than it is going to take to do the dot product, because of those denominators. And those denominators, I mean, look at the vector function we started with. It wasn't that complicated. But that magnitude gets pretty ugly pretty fast. Okay, now we're dotting these guys. So I've got 0 times that, which is of course 0. And then 2 times this. 2 times the 2t is going to give me a 4t in the numerator. And then 2t times this component. If I multiply that 2t in the numerator, I get a 2t cubed over that speed function, which is so complicated looking. This is nice, guys. It wasn't that difficult at all. And I just found the tangential component of acceleration. Oops, I got off the screen. As a function of t. So now you give me a time and I can tell you how much of the acceleration is going in that direction. Or what the component of acceleration is in the direction of motion, which I think is pretty cool. Okay, so that's a sub t. And a sub n is this guy. By the Pythagorean Theorem, we take the magnitude of the acceleration vector, we square it, we subtract a sub t squared, and then we take the square root. So I need this, and I've already got this, and then we're just going to put them together and subtract them and take the square root. So let's find the magnitude of acceleration. Acceleration has components 0, 2, and 2t. So if I want its magnitude, I take the components, I square them, add them, and take the square root. That's how we find the magnitude of everything. But I don't just want the magnitude, I want the magnitude squared. So I'm going to take this square, and I'm going to take this and I'm going to square it. It's going to get rid of the square root. We're just going to be left with 4 plus 4t squared. All right. So that is that part. And now I'm subtracting a sub t squared. So that's all of that squared. Now you might be thinking, I'm still not sure that I want to do this. I promise you it's better than taking the derivative of that component by component, finding its length, and then dividing by it. It's just very tedious. I promise you want to do it this way. If you don't believe me, try it the other way. And if you like it better, you can do it. You're more than welcome to, but I wouldn't want to, personally. So when I square this fraction, I end up squaring the numerator and squaring the denominator, so I've got 4t plus 2t cubed squared. And when I take that square root and I square it, I get 1 plus 4t squared plus t to the 4th. Now over here, in order to subtract these, I need to get a common denominator. Of course, the common denominator between this and this is just that denominator, because this denominator is a 1. So we're going to multiply this guy by 1 plus 4t squared plus t to the 4th over itself to get a common denominator. Doing a lot of algebra here. But this is nice. It's giving us the normal component of acceleration as a function of t, which we can use later for any value of t we want. So it's worth the work. If we distribute 4 times that polynomial, it's going to give me that. 4t squared times that polynomial. It's 4t squared times 1. 4t squared times 4t squared, 16t to the 4th. 4t squared times t to the 4th is 4t to the 6th. It's a lot. I know, I'm sorry. This guy you want to write twice in FOIL, or alternatively you can have the first one squared. 4t times 4t is 16t squared. And then you're going to have 2ab. Remember that formula from algebra? That's a and that's b. We're going to have 2 times this times this. 4 times 2 is 8 times 2 is 16. T to the 1st times t cubed is t to the 4th. Last times last is a 4t to the 6th. We're taking all of that and we're dividing by 1 plus 4t squared plus t to the 4th. And we're taking the square root of this whole thing. Oh my goodness. But at least, yeah, it's just algebra. A little less chain rule than we would have had to do the other way. Okay. Keep going. We're in the home stretch now, almost there. All right, a sub n is, and I'm looking for cancellations. I see that 16t squared. If I distribute this negative over here, it's going to change that sign and that sign. It's going to make that a negative and that a negative. So 16t squared minus 16t squared, those are gone. And then we have this 16t to the 4th and a negative 16t to the 4th. Those are gone. And then this 4t to the 6th and a negative 4t to the 6th. So those are gone. So we actually, don't have much left in the numerator that doesn't simplify. Our numerator is just a 4 plus this plus this. I think I'll factor out the 4 from everything because we can. I have 4 times the quantity 1 plus t squared plus t to the 4th, all divided by 1 plus 4t squared plus t to the 4th. Take the square root of all that. If you want, you could take the square root of the 4 and call that a 2 out front, but you don't have to. It doesn't really make it that much simpler. Okay, and that's our a sub n. And that's nice. It's a function of t. You give me a t value, I can tell you exactly what a sub n is at that t value. So I can tell you how much of the acceleration vector, or what the component of the acceleration is, in the direction that we're turning. It's going to be this much times the normal vector. Okay, last piece. If I'm trying to find n hat, I'm going to take this equation, a sub t times t hat plus a sub n times n hat equals a, and I'm going to solve for n hat. So I'm going to get this guy by itself. Well, I'm just thinking of this as an algebraic equation. I've got this vector on this side. I want to get rid of this vector, so I'm going to subtract it from both sides. And then if I want to get n hat by itself, I divide by a sub n. All right, so I've got my normal. It is the vector a, which had components 0, 2t, or 2 and 2t, and I'm subtracting a sub t, which is actually kind of complicated looking, that times the unit tangent, and the unit tangent was this velocity vector divided by the speed. And the speed ended up in this denominator right here. So we're seeing the speed squared right there now. And we're taking all of that and we're dividing it by this kind of ugly fraction. 2 times the square root of 1 plus t squared plus t to the 4th, all divided by the square root of this guy. Okay, it's just arithmetic from here, guys. Distribute your a sub t through the t, or alternatively you can take those two speeds and multiply them together to get rid of the square root, get the speed squared. So we've got minus 4t plus t cubed all over, oops, that should be a 4th, speed squared times this vector all divided by this. I'm just going to call it a sub n for right now. We're going to do that later. So I'm still working in the numerator. Distribute that guy. Uh, 2t times that is going to give me an 8t squared. Distribute the 2t to both terms. T squared times that, it's 4t cubed, distribute to both terms. You're subtracting those two vectors and you're dividing by a sub n. 0 minus something is just this, but negative. And then I've got 2 minus this for my second component. If I want a common denominator, I can take this 2 and multiply it by that speed squared. So I'm going to have 2 times the quantity 1 plus 4t squared plus t to the 4th minus 8t squared plus 4t to the 4th, all divided by, I'm just getting lazy now, I'm just going to write it as speed squared, just temporarily. And then I'm going to have 2t minus that component over there, and I've run out of space. And I'm going to multiply by the reciprocal of a sub n, I've decided. Okay, so n hat is this, and a sub n was that, so let's flip it and multiply. And that I can factor out a 2t. Here, if I distribute the 2, well, 2 times 1 is going to give me a 2. 2 times 4t squared is 8t squared, and I'm going to subtract that 8t squared, so those guys are gone. And then 2 times t to the 4th minus 4t to the 4th is going to give me a negative 2t to the 4th all over speed squared. And then the last one, I need a common denominator, so I've got 2t times my speed squared minus 4t cubed plus 2t to the 5th, all divided by, I'm just going to leave it as speed squared for right now. Okay. And if you want, remember that's speed. And this is speed squared, and this is speed squared, and that's speed squared. That speed is going to cancel with each of those, so we're going to have a speed in the denominator for all of these. Okay, so I get negative 2t times the quantity t plus, or 2 plus t squared, divided by 2 times the square root plus the one speed that's left after cancellation. So the 2's reduce. I don't think anything simplifies there. Could be wrong. Over here, that's a 2 times the quantity 1 minus t to the 4th. That factors a bit, but doesn't cancel with anything, so we're going to leave it alone. So I've got 2 times this denominator, and then one of the speeds is going to cancel with one of these, so I'm just going to be left with a single speed. Factor in the denominator, and then over here I've got 2t times 1 is 2t. 2t times 4t squared is 8t cubed. 8t cubed minus 4t cubed is positive 4t cubed. 2t times t to the 4th is t to the 5th. That's going to reduce with that one, so those guys are gone. And one of those is going to cancel with that. So I've got a 2 times this, and the speed is this. You might say that wasn't particularly efficient. You're right, it did take us a long time. But it may be long, or may not be as long as it would have been had you had to use the chain rule and the quotient rule on all 3 components of t hat. To find its derivative and then find the magnitude of that vector and then divide t hat prime by its magnitude. Like, that would take a long time. Still trying to simplify here where I can. The 2's reduce. I'm just going to have one big expression under the radical. And that's it. That's n hat. Now if you plug in a particular value of t, you can find n hat at that value of t. So that's the direction we're turning at that time.